Even and odd functions. A function is called an even function if f of x equals f of negative x. The graph of an even function is symmetric about the vertical axis. A function is called an odd function if f of x equals negative f of negative x. The graph of an odd function is symmetric about the origin. Note, a function can be neither even nor odd if it does not exhibit either symmetry. For example, the f of x equals 2 to the x power function is neither even nor odd. Example 12. Is the function f of x equals x cubed plus 2x even, odd, or neither? Without looking at a graph, we can determine this by finding formulas for the reflections and seeing if they return us to the original function. F of negative x equals negative x cubed plus 2 times negative x equals negative x cubed minus 2x. This does not return us to the original function, so this function is not even. We can now try also applying a horizontal function reflection. Negative f of negative x equals negative x cubed minus 2x equals x cubed plus 2x. Since negative f of negative x equals f of x, this is an odd function. Stretches and compressions. With shifts, we saw the effect of adding or subtracting to the inputs or outputs of a function. We now explore the effects of multiplying the inputs or outputs. Remember, we can transform the inside input values of a function, or we can transform the outside output values of a function. Each change has a specific effect that can be seen graphically. Example 13. A function, p of t, models the growth of a population of fruit flies. The growth is shown in the graph. A scientist is comparing this to another population, Q, that grows the same way, but starts twice as large. Sketch a graph of this population. Since the population is always twice as large, the new population's output values are always twice the original function output values. Graphically, this would look like the second graph shown. Symbolically, Q of t equals 2 times P of t. This means that for any input t, the value of the Q function is twice the value of the P function. Notice the effect on the graph is a vertical stretching of the graph, where every point doubles its distance from the horizontal axis. The input values, t, stay the same, while the output values are twice as large as before. Vertical stretch and compression. Given a function f of x, if we define a new function g of x as g of x equals k times f of x, where k is a constant, then g of x is a vertical stretch or compression of the function f of x. If k greater than 1, then the graph will be stretched. If 0 less than k less than 1, then the graph will be compressed. If k less than 0, then there will be a combination of a vertical stretch or compression with the vertical reflection. Example 14. A function f of x is given as a table below. Create a table for the function g of x equals half times f of x. The formula g of x equals half times f of x tells us that the output values of g are half of the output values of f with the same inputs. For example, we know that f of 4 equals 3, then g of 4 equals half times f of 4 equals half times 3 equals 3 over 2. The result is that the function g of x has been compressed vertically by half. Each output value has been cut in half, so the graph would now be half the original height. Example 15. The graph shown is a transformation of the toolkit function f of x equals x cubed. Relate this new function g of x to f of x, then find a formula for g of x. When trying to determine a vertical stretch or shift, it is helpful to look for a point on the graph that is relatively clear. In this graph, it appears that g of 2 equals 2, with the basic cubic function at the same input. F of 2 equals 2 cubed equals 8. Based on that, it appears that the outputs of g are 1/4 the outputs of the function f, since g of 2 equals 1/4 times f of 2. From this, we can fairly safely conclude that g of x equals 1/4 times f of x. We can write a formula for g by using the definition of the function f. G of x equals 1/4 times f of x equals 1/4 x cubed. Now we consider changes to the inside of a function. Example 16. Returning to the fruit fly population we looked at earlier, suppose the scientist is now comparing it to a population that progresses through its lifespan twice as fast as the original population. In other words, this new population R will progress in 1 hour the same amount the original population did in 2 hours, and in 2 hours will progress as much as the original population did in 4 hours. Sketch a graph of this population. Symbolically, we could write R of 1 equals P of 2, R of 2 equals P of 4, and in general, R of t equals P of 2t. Note, the effect on the graph is a horizontal compression. where all input values are half their original distance from the vertical axis.